Good morning. Hello, I can see my students. Hi, hi, hello. Okay, I think we can start. Of course, I have lots of notes on my desk. Okay, that means I hope everybody is good and well, ready to do a little bit of calculus. We still have 2 weeks of, 2 weeks of the instruction, 2 weeks of new material, and then the final review, and then the final week. One thing, because I set up extra homework assignments. I know that you probably noticed this, but this is still open until end of April. But I also supposed to give you one optimization problem, and I did, but for some reason I didn't release. That means you didn't see the question. You can probably revisit lesson 10, not 9, 10. Okay, and you can see one optional quiz, like it's just one question, but I want you to maybe you can upload your solution, or you can type your solution. Okay, and of course you will get some few extra points. That means please still revisit lesson 10. Okay, and it's open. It will be open for 1 week, because it was sitting there, but for some reason, I don't know, I didn't release, I didn't make visible. Okay, that's what we have. We will start chapter 4, and chapter 4 is the second part of calculus, is the integration calculus. We did start a little bit last week, because we did, instead of like differentiating, we were anti-differentiating. We were like recovering a function, having a rate of change. And actually the whole circle, I can say this way, like having a model, having a function, and then finding the rate of change, and then the other way, from the rate of change, recovering the amount, the function. This is, I can write on this slide, is like the whole circle, the whole connection, and it's the fundamental theorem of calculus. Okay? That means we will talk about this, we will connect everything, of course, in the nice, rigorous, mathematic way, I think next week. And that means this week I will just try to introduce, and probably today, maybe tomorrow, instead of anti-differentiating, I can finally say integration. Because that's the same thing. We have a proper name for anti-derivatives, which are, of course, integrals. Okay, but let's start with this section. Okay. So many calculus books, because we are trying to change the calculus textbook, and I'm trying to look at all of different approach in the new textbook. Are you planning to take Math 141? Possibly? Oh, okay. During the summer? No, okay, no, yes, okay. Okay, summer, fall, okay. But I'm assuming also online, right? Through the World Campus. Okay. And I will be teaching, yes, I will be teaching Math 141 in the summer and also in the fall, And as I mentioned, we will change the textbook, but what's happened, because I know that you probably has a textbook, the publisher, that means don't worry, the publisher will provide ebook, like the electronic version, for free. That means you don't have to, because they trying to make, of course, some, I'm not even involved in all of these arrangements, but since we would, because we don't want to ask students to buy another textbook. That's the thing. That means they will provide, if we change the textbook, most likely we will change the textbook. That means everything will be provided for the students that they started and they have the text, because you probably have you have this one. Yes, you have Stewart. But don't worry, I just mentioned this because it's a little bit crazy, but don't worry, will be no extra cost and you will be not asked to buy the second textbook. Okay, that's good. I will see some good students in my summer or fall classroom. Good. The style will be the same. We will just keep adding calculus concepts. Okay, let's start with this areas. And you probably remember I did start the session last week, like asking you about the speed and the distance. That means if we will have, I can maybe write again, let's say my speed is, I think I said 50 miles per hour, okay? And then what will be my distance after like 3 hours? The total distance, the original like this distance, let's say distance travel, of course, 150. And I kind of draw, if this is my speed and this is time, and of course, nobody is like driving with the constant speed, but let's assume that I am driving with the constant speed 50, and then after 3 hours, we can see 150, we know, 150, we know how to compute this, it's just 3 times 50, but mathematically, it's actually the area under the speed velocity curve. Like, I mean, in order to recover, in order to compute the total amount, total distance. That means that's the reason, that we will focus today. And as I said, this is not a problem, because when we have a beautiful, nice rectangle, even triangle, even let's say a circle, we can compute the areas. But the problem is if my speed, for example, will be like, I don't know, like 70, 40, 50, like if I will be driving with, and then we still have to find out the area under the curve. Like let's say after 5 hours. That means what will be my speed after 5 hours if my speed is not always constant. That means that's the exercise for today. That's actually, that's getting 150 from 50, it's actually the anti-differentiation, because from the rate of change, we did recover the original like value, original amount, original function, I can say, in really broad terms. Okay, that's me. Now let's look at the areas. Okay, because that's the point, to find the area under the curve. And as I said, we know the meaning of the areas is not a problem, especially when we have a beautiful straight sides. And I have a few rectangle, everybody knows this. Triangles, everybody knows this. Even if I will have some polygons, we can always try to maybe divide by triangles, add them together, no problem. But we can see nice and straight lines. The problem starts with something like that. And that means that's, we will, of course, we will connect nicely to some formulas and some terminology and the integration calculus, but we can see this will be, that's the point. Having a function, not the constant function, we will have some limits in the horizontal direction from A to B, and we have to find out what is that area, the area of the region under the curve above the x-axis from A to B. Okay. Actually, what do you think? Do you have some ideas? How can we, like so far, the knowledge, the tools that we have available, like how can we compute this? And we will probably, that's what mathematicians, that's what they did before. They couldn't, of course, I can't say, I can't really say, oh, this is the rectangle. I mean, I could start of the curve and at like connecting the curves with the line. Let me, because let's see this one. I just draw this because of course I know the area of the rectangle. That means I can possibly get that value, but it's not, it's not close. And okay, Neil said that we can connect like that. That's what you, The small, yeah, okay, that's me. This will be definitely, this one will be, yeah, will be closer because we will get the area. This is nice. It's like a rectangle and triangle. That means I can get it. And the part that is like sticking out, it's kind of like, yeah, we can compensate for this one. Yeah, we can do this. That's of course, that will be good. Or we can, that means this is still good, but we can definitely, who said we can break this into smaller shapes? That means, for example, I can maybe divide my interval A from A to B to the subintervals, and let's make it easier. Each subinterval will have the same base, yeah, the same width, I can say. That means and we will, of course, we will call delta x this distance. Yeah, but still it's not really. It's good. But what I can try maybe to make it rectangles. Yeah, what do you think? Oh, maybe this one. Oh, I'm not consistent. Still, yeah, I can make the straight lines. That means I can divide by the actually rectangles. Not rectangles, like stripes, and then create a rectangle. We can still see something is sticking above, something is missing below. Yeah, it's still, that means what shall I do? Because this will be a good method to improve this. What do you think? Because I kind of, how many sub-intervals I did create? 1, 2, 3, 4, 5. We can have a teeny tiny. The delta x should be so small, which means we can create. Oh yeah, this is perfect. Infinitely many of these rectangles, and you can imagine if I will have. Oh, of course, they are still too thick. And if you can imagine like infinitely many of them, and now, even if I create a rectangles, yeah, I kind of fit the line. That means this will be the method. We will like slice it, I can say this way, create what we want, create rectangles, find the area of one rectangle and add them together. Yeah, because it will be similar. That means that's it. Yeah, that's the best approximation. And of course, again, if n, let's say n is a number of these rectangles, if n is infinity, it's perfect. It's perfect. Okay? That means actually that's integration. Slicing, defining what we want, defining the areas and adding together. That means adding infinitely many items, let's say general. That's actually integration. Yeah? Like overall, because we have lots of application and you will see, but I think I can say it in really, really basic language that we will always slice something, like define what we're looking for and add all of these together. That's mean adding infinitely many items. Okay, that's integration. Okay, let's keep moving because I do have, okay, we know this. Oh yeah, I typed this because it's not really the same concept. But actually it is. it is kind of like, because you also remember like finding the tangent line. Yeah, we couldn't really find the slope of the tangent. Because how can I find the slope between point and itself, like rise over run, no rise, no run, 0 over 0. That's when we were like approximating through the secant line. The secant line, of course, the secant line was so close to the point of the tangency. That means it was almost 0 over 0, but we know the concept behind. That's when we kind of like approximate. The same for this one. Yeah, the same is kind of like the idea of approximation. Yeah? Okay. And of course, increase the number of rectangles. That means, let's see this. Oh. of course, I didn't want to show you the entire slide, but it's okay. Okay, that means let's see this. Let's use just 4 rectangles, which probably it's not, yes, not enough, to estimate the area under the parabola x squared from 0 to 1. And that's we would want to find out what is that golden yellow region area from 0 to 1 x squared. And since the question is asking us to take only 4, it's okay. And always, as I said, always we will divide equally, because depends on the function. Sometimes the mathematician, they want to have still 4 rectangles, but some of them will be maybe a little bit wider, some of them will be a little bit like thinner. No, we will have the same. That means we know probably you are okay with these numbers, because the entire length from 0 to 1, I did divide by 4. That means the entire length will be, if this is A and this is B, because we have interval from A to B, I will subtract from B to A, like 1 to 0, of course. And then I will divide by N. And this will be my delta X. I'm trying to squeeze. And delta X, of course, is the width, which means 1 minus 0 divided by 4, 1/4. That means I have to go by 1/4. Too many. 1/4 plus another 2/4, 3/4, 4/4. Okay. Okay, that means now we do have our stripes, we have everything, but now I still don't have a rectangles. Okay, that means now it's important moment. How can we create rectangles? I can actually use this, because you can see we still have, the top is like the curve. Now maybe I can pick, I can pick the first sub-interval from between 0 and 1/4, okay? That means we will always have sub-intervals, okay? And we will always look at the beginning and end. 0 is the beginning of my interval, and 1/4 is the end. Initial point, terminal point. And now we will call, like common sense, that 0 is placed on the left-hand side, and 1/4, we can say I'm looking at here, from 0 to 1/4. That means 0 is on the left-hand side, and 1/4, of course, is the right-hand side, okay? And we can also because we can also nicely define maybe the middle point, but we will focus in this class only on the left-hand side, on the right-hand side. And now I will pick what I did. Okay, let's pick the right. And I can pick one of those. That means I will pick the right-hand side endpoint, okay, to create a height of the rectangle. Okay, that means 1/4, I have to draw a line and meet the function, maybe green. Draw a line, meet a value of the function, and this will be height of my rectangle. That means my rectangle will look like that. Of course, not perfect, but I have to be consistent. Yeah, I can't jump, I will just follow. That means what I'm doing, I divide by 4 rectangles, and I'm picking the right-hand side endpoint to create a height. Now let's jump to the second, S sub 2, like the second region. Now, of course, everything changed. I can erase this, because now I have 1/4 and 1/2. Which of the endpoints is on the right-hand side? Can you tell me? Of course, now it's 1/2. 1/2. That means 1/2. Okay, 1/2 is on the right hand side, focusing on the second, and then I will draw a line meeting the value of the function. You can see the top green dot is the value, and this will give me a height. Okay, because I need a nice horizontal line. And then, of course, keep doing the same way. 1/2 and the 3/4. 3/4 is on the right-hand side. That means this is on the right-hand side. This is the corresponding value. and that horizontal line, the dot, will give me the height of my rectangle. And 1 is on the right-hand side, the corresponding value is here, and this will give me the height. Okay, that's the way. Of course, what I can do, I can also pick the left-hand side endpoints and create the rectangles. I think we can do, I have the other slide and we can do the left, okay? But we can see that's the way to approximate. Of course, 4 is not enough. Yes, 4 is not enough, but still, if I will get this areas of all of the rectangles, I think it's still kind of like, yeah, approximation. Lots of my rectangles, I mean the part of the rectangle is sticking out, but still. Okay, and let's try to write, can I write? Oh yeah, I can actually write here. That we know how to find the width, which is delta x 1/4. That means now the area will be, okay, let me just put it this way. We have to add 4 of them. Okay, and then we will have delta x, okay, because delta x is the base, because of course it's base times height. It's just the rectangle. That means delta x is the base of the rectangle, and the height will be the value of the function for the point on the right-hand side. And again, delta x, and the height will be value of the function of the point which was on the right-hand side. And I can keep working. 3/4 was on the right-hand side, and the last one is value of 1. Okay, that means base times height, base times height. Of course, base is the same. That means that's good thing. Delta x, which is the base. Shall I write it somewhere here? That's delta x, and it's 1/4. I can factor out. And then the value of the function x squared at 1/4 will be 1/16 plus 1/4 plus 9/16, and 1 squared is 1. That means I did square the numbers just because of the function. And delta x, actually, I can put delta x, the actual value, 1/4. Okay, 1/4 squared, 1/16, 1/4, 9/16, 1. No? Shall we do the arithmetic? I think I have on my other slide. This will be 4/16. 4 plus 1/16 will be 5. 5 plus 9 will be 14. And this is 16/16. That means 14 and 16, 30. I don't know if I have this right. And then 15/32. If you can, yeah, like if I will get the common denominator, 1/16, 4/16, 9/16, 16/16. Adding all of the tops, the numerators, we will get 30/16 times 1/4. I can simplify by 2, 15, 16 times 2, 32. Okay, 50 is like around half, a little bit less than half. But now I can ask you, did we overestimate it or underestimate it? What do you think? This value, definitely over. Thank you. Thank you, Matt. Because we can see this 15/32, less than half, but it's definitely even less than this, because that's the area of the green rectangles. Okay, that's, we can see that's one of the procedure. Let's maybe choose the left-hand side endpoints, yeah? And maybe we can take the average. Yeah, that's kind of like the way, because definitely taking the left-hand side, we will underestimate. Let's see. Oh yeah, I have nice, beautiful, that's the right-hand side or the left-hand side? Yeah, because now it's Oh, left, right. We can check the height. That means the height of the first one is here. The height, that's the height of the rectangles. And we can see the height looking at the specific subintervals are from the right-hand side. That's mean definitely the right-hand side sum. Yeah, no, it's fine. It's okay. And did I type everything? Oh, yes, I did type. That's we can see we know where the numbers come from. Yeah, definitely over, because we're just looking nicely. Okay, but I could pick like 100 rectangles, but that's not a point because we will repeat the same procedure. I just want you to know how we come computing. Okay, let's do the left. Oh, okay, I did use the calculator. Do I have the left? Yeah. Oh, too fast. That's we can, let's see. This will be my first subinterval, and actually 0 is on the left-hand side, which 0 has the value 0. That means it's nothing. Yeah? The base is still 1/4, but times 0 is 0. Yeah? It happens that we have no actually rectangle. And then 1/4 is on the left-hand side for the second subinterval. 1/2 is on the left, and 3/4. And this is creating, these heights create my rectangles. That means definitely is the left-hand side. You can always look at the rectangle, find the height, find the height, and you can see if it's on the left or on the right-hand side. That means it's definitely the left-hand side. And we will follow that 0, the same procedure. And I think I have it. 1/4 times 0, 1/4 times the value of the function for 1/4, 1/4 times the value for 1/2, and 1/4 times the value for 3/4. And we can add together the same thing. And we have some, okay, Matt is saying that the heights are all values from the right-hand side, just shifted over 1. Actually shifted, not over 1, shifted like that delta x. Yeah, I don't know if I understand. It's 1 unit. Okay, I don't know if I understand, but if I do understand, I think we shift just, okay, no, it's fine. We know, we don't worry, we have time. We can always, I don't know what's the easiest way. Let's say this is my subinterval, right? That means we can see 1/4 is on the left, 1/2 is on the right-hand side. And if you like to define this way that we shift something, I would say that we shift delta x units. Yeah, not really 1. Delta x could be 1. We can jump by 1. Some of the questions, I mean, in this case, we're just jumping by 1/4. That means I think we jumped 1 delta x units. Okay? Yeah, okay, okay, good. Okay, that's we can see this one. If we look at the rectangles, the golden part is definitely underestimation. Yeah, that means the only thing at the moment that I can do, I can say my actual area under the curve is between 0.2 and 0.4, 0.5. Yeah? I can add them together and get the average, but it will be still not really perfect. But we know what is the problem. Do we know what's the problem? What quantity shall I change? It is underestimation, but overall, the previous was the height. No, I can't really change the heights because the function will stay the same. Something that not enough intervals, something that we actually choose. We have to have, that's too little, like just 40 or 400. 4,000, and then adding them together, then I will perfectly fit the line. Yeah, and okay, that's, we don't have to take any notes. I can just show you. It's everything. It's in your textbook. That's you can. Let's see this one. This one is just 8, and looks better. The left and the right hand side. That's the left hand side endpoint. That's the right hand side endpoint. Yeah, because we can see on the left, the height is on the left. The height is on the right. Okay. Now let's look at this. And doing this calculation, we know how to do. We can add 8 of them. We have 2.27. I mean, 0.27, 0.39. Yeah, it's getting closer. You can probably approximate, but let's look at even more. What's the amount of rectangles? 10, 30, 50. Yeah, 50. So nice, so beautifully fitted. And the top row is right hand side, the bottom is the left hand side. And you can even see sometimes we use like a R for the right hand side and L for the left hand side. And the subscript means like the number of these rectangles. Yeah, that means that's the point. A number of these rectangles, number of these stripes. Of course, the perfect approximation is infinity. Yeah, infinity. That's what we have to. Yeah, we have to include and define. As soon as infinity is involved, we will have a proper definition. Yeah? But that's integration. Yeah? Like overall, if you will finish this class and just somebody will ask you like, what is integration? You can say slicing and adding together. Yeah? Something like, because having having a model, a problem, having a thing like in the whole, like we don't know what to do sometimes. Yeah, like one of the, we will actually do in Math 141, Calculus 2, like one of the application is of integration is, for example, having a loaf of bread, like the nice proper bread, not the square one, not the fake one, nice bread from the oven, and finding the volume of the bread. Yeah, like it's not regular shape. How can I find it? But when I slice the bread, when I have one slice, like slice of the bread, kind of reminds me like a cylinder. Having the volume of one of them, I can add all of them. Yeah, something. That means whatever problem we have, if we can slice it and we can focus on one small item and then add them together, that's integration. Okay, do you know the symbol for integration? Do you know? Yes, long S. What this means? Yes. You see, that's summation. That's the big long summation because we're adding everything, all of the slices of the bread, all of the rectangles. Yeah, that's nothing else like addition. Summation. Okay, let's keep working. Oh, what we have? Okay, I have some numerical values, but we don't. Actually, because we didn't even, let's look at this. This is 0.38, 0.35, 0.34, 0.28, 31, 32. That's when you can probably assume what will be the actual value. I do have a table. You just saw it. That we can see left-hand side, right-hand side, and number of rectangles, 10, 20, 30, 50, 100, 1,000. That means probably we tending to get 0.3, I would say 0.3. We will have a nice proper way to get it, and we will get, it's 1/3. Okay, yeah, it's definitely, maybe even today. Okay, let's see. Because actually tomorrow evening, I will introduce the proper definition. But we still have a few formulas today. Oh yeah, that we can see this is definitely, if I will pick, I just pick the right-hand side. But if I will pick the right-hand side endpoints, I can have even the left. We will get the same. Number of rectangles is of course infinity. Yeah, but we will focus on, that means the R means that we're adding all of the rectangles with the right-hand side endpoints as a height, and n of them, and n is infinity. That means then will be a proper number. But we still have to nicely define this. Yeah, we have infinity, that's good, but we have to still define it. Because I will not write infinitely many times, like delta x times the value of the function for, I don't know, 1/100th, and then plus delta x times the value of the function for another one. No. We have to have a nice, probably, what do you think? What symbol will be involved when we adding similar items? Do you know from the Greek alphabet? Sigma. Sigma is telling me that we will be at similar things. Yes, that means definitely a sigma. Yeah, is important. And actually, what we adding, because we remember the area of one rectangle was delta x times the value of the function, and let's say x sub n, because that was some. We could pick the right, we could pick the left-hand side, but we will call a sample point. That means actually this is just like the base times height. That's the area of one rectangle. And adding all of them together, I can say that this is delta x base times the height, value of the function for the sample point, and n is changing from 1 to infinity. Or maybe too fast. I do have this, let me remove infinity. That means I will just call x sub I, yeah? And I is changing from 1 to n. That's a little bit better. And actually that's how we will define, because we can see it's just the area of rectangles. Delta x is the base, value of the function is the height, base times height. And sigma is telling me that I'm adding all of them together from 1 up to n. Yeah? And of course, I have to place the limit in front to indicate that n is infinity. Yes, that means, I did squeeze. As always, I'm trying to do this, the whole section in one slide. Okay, but let's keep working, because I draw a nice big sigma for you and I was explaining everything. Okay, but you know the idea, I'm sure. Okay, that means this one is what I have. That's okay. I have this. Okay, that's, we will need few formulas. That's what I'm introducing this. That we definitely know that the entire width of the interval, because that's what we need. We also have to know where we are. We are from A to B. And I hope you okay to indicate like the number of units between A and B. Like, let's say, what will be the number of units between 2 and 13? What is that? Oh, a little bit. Of course, it's 11, but how did you compute this 11? I know. Like mathematically, yes, we took the, yes, we took the bigger value minus the difference, of course, yes. That's, we can see the same thing, B minus A. Okay? The thing is, we will not, typically we will take the bigger value minus the lower value, and we will always get this number positive, greater than 0. It's the length. It's like a common sense. Geometrically, it is greater than 0. But please remember, never put the absolute value, because absolute, if for some reason B is smaller than A, we will get negative number, but that's later, okay? For now, everything works geometrically, common sense. Okay, that's you okay with B minus A. Now, are we okay with this formula? The entire number of units divide by n. Perfect. That means that's how we will compute delta x. Okay, the entire interval dividing by n. And then, of course, then we have the sub-intervals, x sub 0 to x sub 1. That's the first one. From x sub 1 to x sub 2, from x sub 2 to x sub 3, and so on. Yeah? But the good thing is to remember that this is the beginning, x sub 0, and this will be the end, x sub n. Yeah? Okay, and now, what else we have to, okay, that means it's two, of course, it's too many values, right? Like x sub 1, x sub 2, x sub 3, that's too much. What we would like to do, we would like to define each of these sample points, because that's the sample point, that's the sample point, all of them, just in terms of A or B and delta x, because delta x will be always given. I mean, oh, no, we can compute. We can always compute delta x, no problem, having A and having B. Yeah? No problem. That means now let's think, how can I define the first sample point? If this distance from 0 is A and this distance is delta x, that means how can I define x sub 1? How many units away I am from 0, reaching x sub 1? Can I say A plus, yes, that's it, A plus 1 times delta x. What about x sub 2? A plus how many deltas? Delta x? 2. That means we can nicely see how number of delta x corresponds to that index, the subscript. That means x sub 1 again will be A plus 1 times delta x sub 2 will be A plus 2 times delta x, and so on. And I do have here. Okay, that means this is how we will define. And of course, x sub n, that's what we will need, because we will not, like, x sub n will be defined like any sample, I mean, no, not any, sample point will be defined as a plus n times delta x. And you can probably, you probably realize that I'm only talking about the right-hand side, because I did define the x sub 1, and x sub 1 was on the right-hand side. X sub 2 is also on the right-hand side. When I look at my, if I would like to eventually create my rectangles. Okay, that we can see. And that's what we will do. We will not play with left-hand side and all of these formulas. Okay, that means I can make some stars. That means we will definitely need this. Okay, we have to know this, and we have to know this. That's quite important, because we will play with these formulas. Okay, that means you know a lot. And of course, n is infinity. Yeah, n is infinity. Okay. Let me change it. We will see these formulas again in different. Okay. That's me now. I think I did wrote this, because I'm tending to introduce the sigma notation. That's me now having the, and we will call x sub. I will come back for 1 second to the previous slide, because this is x sub n, but sometimes you will see x sub I, because what I need to say that I is defined from 1 to n. That's me, I'm kind of holding that n label for, but x sub I or x sub n doesn't matter, the same idea. That we can see the area of the rectangle will be the base, which is delta x, that's actually the base. And the height is the value of the function at the sample point, x sub 1 or x sub 2 and so on. And then when I add all of them together, I have my approximation. And in this case is, I can maybe say this way, using the right-hand side endpoints. And we will focus mainly on the right-hand side. Unless I'm giving you so little like rectangles, and then I will ask for left-hand side. But if the infinity is involved in the lots of rectangles, we will always focus on the right. It's a little bit easier to define everything. Okay, and as I said, we adding similar terms. That means we will not list them like that. We will use the sigma. As we can see, the best is when n is infinity. We know all of this. And I will add infinity to this sum. That's we can see the area. We know that. I still have my left. And we know what it is. It's just the area of the first rectangle, the area of the second one, the area of the last one. But we do have infinitely many of those. Yeah. We can see left-hand side, we have to start with x sub 0. But no, as I said, we will mainly focus on the right-hand side because of the formulas. Okay, and now we ready. Again, I have, okay, because I took everything from your textbook. You can look at this, but we don't, yes, please, as I said, I will not make your life complicated, because we may pick, of course, having a sub-interval, picking the right-hand side or the left-hand side is the perfect. Sometimes we can pick exactly like the sample point in the middle. Or some of the mathematicians, they think it's not even enough. They trying to pick like whatever is the most optimal like value. Let's look at these blue lines. The blue lines are kind of like they are sample points. And they are really random. I will not find the nice proper like formula pattern. Yeah, like wherever we're looking at the curve and wherever is the optimal like height, we will pick. And that's mean if you will see like a little star, this means they are really like a sample points somewhere. No nice formula to find this. Oh no, a little bit crazy, but it's something like that exists, but we will not use it. No. Yeah, just sample point. We will focus on the right-hand side. Okay, and then sigma notation. Oh, okay, that's my entire slide. That's my entire slide. That's what we will use. Okay, we know what delta x means. It's the base of this rectangle. Value of the function f of x sub I is the height. That means it's just base times the height, the area of the rectangle. And sigma means that we adding all of them. That's what we will use. If n is infinity, we will always use sigma. If n is just like 4 rectangles, we can just list them. 1, 2, 3, 4. Yeah. But this is, of course, the sigma notation. And now we can see underneath the sigma, yeah, we do have an information what we're starting with. And of course, like this will be normally, it's a counting numbers. Yeah, like I'm counting the first rectangle, second. That's when we will start with 1. I is 1. And then it's 1, 2, 3, 4, 5, n. And we will end with n. And of course, the sigma itself is telling us that we're adding. Yeah? Sigma means adding. Okay, and this one represents the right-hand side. Okay, because we can see we're starting from x sub I. Yeah, we're starting with the first one. We're not choosing the 0. This will be the left-hand side. Oh, the left-hand side. But as I said, we will mainly focus on, and this one are just the sample random points, wherever we would like to think, which if we will have infinitely many of them, that's time consuming. We will not do this. We will focus on the right-hand side. Mainly. That means if you will see some formulas that I'm asking, probably is always x sub I, which means we're starting with the first one, second one. That's always on the right-hand side. Okay, that's the sigma. Okay, and maybe we can do, okay, let's see. Oh, if you, I know I can see you that you're taking the notes, but you know that I will I will, yes, provide this. Oh, I always rewrite my notes, always. It's better when we have, yeah, the handwriting. Oh, I can see that Yatniel is still writing. Okay, no, it's okay, it's okay. We just, yeah, it's nice. It's like in the classroom. I will walk between the desk and I always wait. If the students are taking the notes, always. Oh no, I can organize additional session and finish up rather than hurry up and no. Okay, I will move the slide now. Okay, I have a nice story, but I don't know, is this, okay, I can skip that slide, or maybe not. Okay, that's me now. This is just I mean, not just, oh no, formulas, sigma notation. But now let's just look at this, just the sigma. Like for example, if I will have n, and n, let's say like this. I would like to check if we understand the sigma notation. That means we have just n, sigma is telling that I'm adding, and n will change from 1 to 5. That means, do you know how can I expand this? What this means? You probably know. Of course, 1, because that's my n. 2, we always go by 1, it's counting numbers. 3, 4, and I have to stop at that number, 5. Yeah. And then I can add. And for example, from 1 to 100, of course, we know what this means. And yeah, that's what I have on my other slide, because we do have lots of famous mathematicians, but one of them is name is Gauss. Carl Friedrich Gauss is the German mathematician. And I don't know if it's maybe it's a real story. When he was a little guy in, let's say in the elementary school, his teacher actually asked, I don't know if she used the sigma notation, but she asked the students, can you add all of the numbers from 1 to 100? Yeah, like 1 plus 2 plus 3. That means she probably thought, oh, they will be sitting and counting, and now I have time. And of course, as always happens, one boy raised the hand and he said the answer, like after like, I don't know, after a minute. And she said, wow, how did you do this? And do you know what he did? And he, of course, he came to the blackboard and he explained, and he did something like that. Yeah, like from we have to add the numbers from 1 to 100. That's the reason that now we do have a formula for this. Okay, let's see. Oh, am I messy? Okay, that's the exercise, right? From 1 to 100. That means he took all of these numbers. Now he took them and he reversed them. Okay, 100, 99, 98, 97, and so on. And then when we add them together, what is this sum? What is this sum? What is this sum? Can you tell me what is 100 plus 1? What is 1? Of course, each of them is 101. Yeah? And how many of these 101 we have? 100. That means we have 100 times 101. But do you think, and it's easy to multiply, right? Because I can, no. I can only add 2 zeros, which is this. But is this my sum or is something too much? What I have to do to get actually, because 101, it's a double, right? Because we can see I have 2 rows, and she only asked, yes, that we have to say times 1/2, dividing by 2. 10 divided by 5, I mean 10,000 is 5,000, not 50. 5,050, right? 5,100. Okay, that's the answer. Yeah, that's what he did. Yes, 10 divided by 2 is 5, and 100 divided by 2 is 50. Yeah, that's what he did. That's me. Now let's see, because that will be the formula. He was asked to add 100 numbers. That's mean n. N is 100, and he multiply by one number more and divide by 2. That means this is actually, oh, I have this. This is the formula. Now, if you would like to add 5, you can put 5 times 6 over 2. It will be the number. If you would like to add 20 numbers, 20 times 21 divided by 2. Yeah, you don't have to add them together. That's the formula. And this was apparently discovered by the little Karl Gauss. You probably, I don't know, I'm pronouncing like in the German way, but I think it's Gauss. Gauss. Oh, I think it's double S, or maybe it's the Gauss. Okay, that's me. Just like a little story. But it's nice to know when we adding this, yeah, we can replace with this formula. That means the formula looks kind of like a finite, because, and n could be any number, of course, yeah, rather than having a sigma, because sigma is always like, I will always think that I have this a few terms, and then I have dot, 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 and I have the last one. That means how can I manage, where is my pen? Oh, sometimes I'm losing it's okay. Like, how can I manage the dots? How can I manage sigma? But if it's this, just the counting numbers, adding them, we can use this formula. I think it's Gauss. Oh yeah, that looks better. Okay, that's when because I will probably not ask, but it's for this formula, but it's worth to know. If I will ask, I will provide this formula for you. But let's see, because we do have, oh, I have my writing. Okay, that's when we also have a formula for adding the squares of the numbers. But this formula is, it's not easy to prove. Oh, it's a little bit more crazy. But the same thing, if you would like to add the squares of the counting numbers, you may use this formula. And I also have cubes. Okay, but as I said, we don't have to. Why I don't see my pen? Let me do this way. Now I can see, now I can't erase, great. It's okay. Okay, that we can see, we do have like 3 formulas. And the only thing is, the definition of the integral will involve sigma. And if the function is just x, or x squared, or x cubed, yeah, we will actually need to rewrite, we will need to use these formulas. Okay, like adding, like if the function is like just x, or maybe x squared or x cubed, yeah, and that means we will have this inside the formula. But I will let you know. Yeah, I really want you to know these formulas, but as I said, I will definitely indicate when we need. Oh, I can't erase this one. Okay, let's do maybe one thing and we will finish. Yeah, it was nice introduction to integration. Oh, what I have. Oh yeah, that's again the formulas. Because it's fun to compute the integrals based on definition. Like, do you remember the definition of the derivative? The long limit way? Probably you didn't like it because you prefer the formulas, shortcuts, yeah? But it's the same way. We will have formulas, we will have shortcuts, but it's also nice to know the definition. But let's see. Oh, I do have a few sigma, but sigma is just addition. That means it's not a few properties. When we have a constant and the main function, we can place the constant in front, focus on the main like formula and expand it. When we have addition, we can simply have the addition of 2 summation, and the summation of the difference is the difference of 2 summations. Yeah, kind of like distributing. No problem at all. Or probably we will keep together. We don't even have to.